Today we're going to go a little farther with sine curves. So I want to remind you, yesterday we learned about period and frequency, very similar terms. Period tells you the time for one cycle, and frequency tells you the number of cycles per second. The best way to get them is when you have lots of cycles, is to start at some spot. Probably the best would be where the sine curve starts, or at least someplace easy to notice. And then count off your cycles. So I started at the bottom. That's 1 cycle, 2 cycle, 3 cycle, 4, 5, 6, 7. So I have 7 cycles. That would go in here and here. And the time is about 3.95 seconds. And I'd put those in for time. When I solve for period, I would get the time in seconds for 1 cycle. And when I solve for frequency, I get the number of cycles per second, and that's called hertz. Okay, first new thing we want to learn is the vertical shift. So I'd like to show you guys when we have this sine curve being produced as our ball swings back and forth away from the pocket lab. What we mean by vertical shift is we mean how far is it from the pocket lab to the ball when the ball is straight down. So this distance here is our vertical shift. That distance, if we can watch this happen again, would be the distance to the very center of that curve. So if we were to draw this out, this spot right here that you see happening right now as the ball hangs straight down, that is the vertical shift. So in this case, it's 40 centimeters. It's 40 centimeters away from the pocket lab when the ball is hanging straight down. That's what we mean by vertical shift. Okay, then we want to talk about phase shift. And for phase shift, what we look at there is where in its cycle is the ball when you start timing. So again, where in its cycle is the ball when you start timing? This is a perfect sine curve. A perfect sine curve is one where you draw that horizontal bisector that we just talked about, the vertical shift, and then the sine curve starts right on that vertical shift heading toward higher numbers. That is a perfect sine curve, and that is a shift of 0. That is no phase shift. That's a perfect sine curve. Okay, I want to show you how you get a perfect sine curve. So you'll notice I started collecting data and I was not going to get a good sine curve. So what I do instead is I wait. And when the ball gets to the straight down spot, watch the sine curve, I hit collect. And if I start collecting when the ball is at that straight down position, I'm going to do it again. Boom. I will get it with no phase shift. Again, that's a phase shift of 0. A perfect looking sine curve where it starts on that middle line heading up and then comes back down again. Okay, a phase shift of 0. Okay, so there it is. Phase shift of 0. You start collecting when the ball is hanging straight down, moving away from the pocket lab. Now I'd like to get a phase shift of what's known as pi over 2 or 1.57. Or sometimes you'll just call it a cosine curve. So what you do is now, when you hit collect, you do it when the ball's farthest away. You start collecting your data when the ball is the furthest possible distance from the pocket lab. And then it will start at its highest point. Okay? It will trace out a curve just like it did before. Some people will call it a cosine curve, but it's really still a sine curve with a phase shift of pi over 2 or 1.57. It's just like a sine curve. You just hit collect at a different moment as the ball swung. You hit collect when the ball was farthest from the pocket lab. Okay, and it looks something like that. Okay, the next phase shift we want to learn is a phase shift of pi, or 3.14. And this time we're going to hit collect when the ball's straight down, just like before, but heading towards us. So again, don't click there. You click collect when the ball's heading towards you. And then it will start at the midpoint, and it will be getting closer and closer to the pocket lab, and then farther and farther from the pocket lab. Again, this, some people would call that a negative sine curve. It's a real sine curve though, with a phase shift of pi, or 3.14. It's all a matter of when you start collecting your data. And it would look something like that. Just like a regular sine curve, but upside down. It's a phase shift of pi, 3.14. The final phase shift we want is 3 pi over 2, or as a decimal, 4.71. And this time we hit collect when the ball is as close to us as possible. And you see it tracing out. So again, you'd hit collect right now. The ball is then at the closest distance to the pocket lab. It moves away from the pocket lab and it comes back to the pocket lab. Again, this is a phase shift of 3 pi over 2, decimal 4.71. And again, it starts at the closest position to the pocket lab. So here are all 4 of them at once. The phase shifts again are 0 for the one in the top corner. You hit collect when the ball was midway through, heading away from you. Here, it's a phase shift of pi. You hit collect at the exact same spot, but now the ball was heading towards you. This one was a phase shift of pi over 2. My bad. Phase shift of pi over 2. Again, 0 and pi. And this one is a phase shift of 3 pi over 2. Decimals, 1.57, 4.71, 3.14. All right, so that's the phase shift. So we have vertical shifts, we have phase shifts. The final thing we have is what's called the amplitude. And the amplitude just tells you how far the ball swings away from equilibrium. Straight down is the equilibrium, so how far does it go to the right? How far does it go to the left with reference to that equilibrium spot? So as we watch it, and it swings back and forth, we draw our bisecting line, and the amplitude is just how far did it go in either direction from equilibrium. Here you can see I ran it again. It's not swinging as far this time. I pulled it back to a smaller angle, and you can see it is a much smaller amplitude than it was before. Amplitude again tells you how far it went from equilibrium. How far did you pull the ball back? Later we're going to see it tells us how loud a sound is, how bright a light is. It's going to be a very important quantity in this unit. So make sure you understand it's how far it is from here to the top. Okay, so you can see I got 4 different sine curves. They're identical in every way, shape, and form, except for amplitude. We have a small amplitude, and we have a large amplitude, and we have some in between. The way that you find the amplitude again is you bisect your curve. That happens to be at 40. You see how high up it goes, which is about 11 centimeters up and about 11 centimeters down. The amplitude would be 11. Okay, how far up, how far down, that's amplitude. It's measured in centimeters. Okay? Finally, we'd like to put it all together So when you try to generate a sine curve, this is the equation. Y, that represents the position. T, that represents the time. A represents amplitude. D represents the vertical shift. C represents the phase shift. B is the tricky variable. B is determined by the period and the frequency. Okay, so one more time. D, vertical shift. A, amplitude. C, phase shift. B is determined by the period or frequency. Both, really. And to find the B value, you take the frequency and multiply by 2 pi, or you take 2 pi and divide by the period. They will both give you the exact same number. Okay, so I'd like to actually do one with you. You'll do 2 more of these on your own, so please make sure you see how this works. I'd like you to take that graph and figure out the D, the A, the C, and the B. Okay, so the way you do this is start with the D. I think that's the easiest. Same as I've had with all of them. Find your D by cutting the sine curve in half. Make sure that half is above and half is below that line. So for us, the D would represent 40 centimeters. 40 is the bisector for that curve. Amplitude. How far above and below 40 do we get? Well, you can see we're somewhere around 56 is the high. So that would mean an amplitude of 16. Again, amplitude is measured in centimeters. Next, we look for phase shift. We have 4 primary phase shifts. We're starting at the lowest value. Our baseball is as close to the pocket lab as possible. That corresponds to 3 pi over 2. We can write that for our phase shift as 4.71 radians. Boom, we're done 3 of the 4. The 4th one is the tricky one. The 4th one, you have to determine your frequency or period. So start it somewhere on your graph. Count out a few curves. 3, 4, 5. I'm going to do 5 because I'm right on the line. So I have 1, 2, 3, 4, 5 curves, 5 cycles in 2.8 seconds. 5 cycles in 2.8 seconds. I divide, I get my frequency. I take that frequency and I multiply it by 2 pi. That's what goes in as my B. And that is measured in radians per second. I hope I didn't go too quick, but if I did, rewind, make sure you understand how all this works. I'm going to ask you to do 2 of these. One that I laid out for you, and one that is generated randomly for you. Okay, so I will see you guys tomorrow. If you have any problems, don't hesitate to reach out to me as always, and hopefully we will be back together soon.